Hello. So this is another video. Today we're going to talk about calculating final concentrations of the H plus ion. So uh, let's start with a simple equation and talk about it through steps. So one thing we're going to add into here is time. We're going to talk about how we go from an initial concentration through a process, then we get a final concentration. And in this process, a set amount of time happened. Like I added things together, I waited for a minute, then I had two new products. Now, this amount of time in between, the lowercase t, this can be in seconds, this can be in hours, whatever. We'll talk about that later on in the next chapter called kinetics. So, let's get started. Here's a quick example. HCl plus NaOH. Now, what does this equal? Well, first off, we know the ionic equation. H will split apart from chlorine, producing ion forms. Sodium, positive, OH, minus. Now, that separation takes some time. And then things are going to start to happen. And over time, eventually, this hydrogen will bond with this oxygen and produce water. And then this chlorine will bond with this sodium in this double replacement reaction and produce sodium chloride. Cool. Well, if I produce these two new compounds, how many compounds am I left with? Well, over time, I'll be left with almost, in this example, I'll be left with 0 reactants and only the two products. So I can go back and kind of this one is what I consider an initial, and this would be final. So what the difference is that we started with reactants, went through a set amount of time, and produced two new products. So if I looked at the concentrations, well, this would be 0 moles, right? I also have 0 moles here. And of course, 0 and 0. So what we're looking at here is the formation of new things from old things, with no old things left. I hope that made sense. Okay, let's add some numbers and add some math to this. So let's talk about CaOH2. What will that decompose to? And if I have initial concentration of 0.1 moles, I'm going to put a little I over here to represent its initial concentration of 0.1 moles. Well, how many moles of products do I have? I have 0 moles, and I have 0 molars here. Excellent. Okay, so net ionic equation, our calcium breaks apart. Eventually, I produce calcium ion plus 2 OH minus. Now, I have nothing left over here. So my final concentrations, well, I have 0 reactants left. And how many moles of calcium do I have, and how many moles of hydroxide do I have? So that's the big question. How do we find how many moles we have? Well, we did stoichiometry. We can do that. Given 0.1 moles per liter of CaOH2, times my molar ratio. Now, if I look back, I have 1 mole of CaOH to 1 mole of calcium ion. All right, and we can solve that. That gives us 0.1 moles, or moles per liter, molarity. Excellent. So let's go back here, let's fill that in. 0.1 moles. Let's do the same thing with OH. If I have 0.1 moles of CaOH2, my molar ratio is 1 mole CaOH2 to 2 moles of OH minus. Where did I get 2? Well, I have 2 here. So that's important. I have 2 moles here, and that's what I'm using for my molar ratio. Excellent. And 0.1 times 2 divided by 1, 0.2 moles per liter. Awesome. And so my final concentration of hydroxide ion, 0.2 molar. Excellent. So that's pretty messy how we went around here. So quick review. We started off with an initial concentration of 0.1 molar CaOH2. And eventually, we created, through the magic of chemistry, calcium ion and 2 OH minus hydroxides. Using stoichiometry, we calculated how much we made. We made 0.1 moles of this and 0.2 moles of that. Excellent. Well, part B of the question. Let's see. What is the pH of the final solution? Okay, well, let's figure out what we have. We're looking for pH. Now, what we know from about pH is equal to the negative log of the hydrogen ion concentration. Okay. Also, pH plus pOH equals 14. Now, if I look back at my equation here, we don't have H+, but we do have OH-. So I'm going to calculate the pOH based on the concentration of OH-, and then I'm just going to subtract that from 14 to get the pH. Excellent. That's a good plan. So over here, write down some steps real quick before I get ahead of myself. 1, find the concentration of OH. 2, calculate the pOH. And 3, subtract from 14. Excellent. So I have 0.2 moles per liter. That's a concentration. That's what I'm using. That's my OH-. Okay, so what is my formula for pOH? Negative log of OH-. So what's the negative log of 0.2? Well, fancy calculator. Can you imagine doing chemistry without a calculator? Terrible idea. That equals about 0.7 on the pH scale. That is my pOH, okay? So that's number 2 over here. So I found my OH, I calculated my pOH, now I'm going to subtract that from 14 to find my pH. So pH, put that right, maybe I'll put it over here. pH is also equal to 14 minus pOH. So 14 minus 0.7 is equal to 13.3. Excellent. Now 13.3, that might ring a bell. That means it's an extremely basic solution. That means there's not very much leftover protons. There's a lot of OH. Now if I look back at our original equation, CaOH OH2 yields calcium plus 2OH minus? Well, yeah, it's a basic solution. I have a lot of OH minus over here. So that makes sense. If I would have gotten something like 1.8 times 10 to the negative 6, that doesn't make sense. Having it be a pH of 13.3 in a basic solution fits perfectly. Okay, so here's a quick picture of that. This is an excellent question. I really like to ask these questions on quizzes and tests because they apply a lot of different aspects. It uses a little bit of stoichiometry, initial and final concentrations, some pH and OH. Hint, hint, you have a quiz on Thursday. Excellent. Study hard. We'll talk about this tomorrow in class. Have a great day. Bye-bye.